Today I'm going to be deriving backpropagation for a linear layer, but in matrix form. Now, and then this is, for the end goal of being able to write down the Python expressions to be able to do backpropagation for a linear layer. This is something I've done, several times. I've done it way back when I first started learning about neural networks. And I find myself having to look at this every 6 months or so. And I find myself getting very tangled up in tracing the indices. So for me, as much as for you, I think that this video is going to be useful. I'm going to be able to look back at it at 2x speed whenever I want to come back to this topic again and just quickly remind myself of how to do it. So without further ado, a linear layer looks kind of like this. So you have the outputs y. This is by the way, y is a matrix or array if you want, which is batch size by some feature vector dimension n for y, right? Equals xw. So x is also batch size by now m, some other feature vector dimension. And w is a weight matrix, which is r m by n. So it's just like a m by n matrix. And the reason I put the w on the right, I'm right multiplying it, is so that I can have it as an m by n matrix rather than an n by m if I was like left multiplying it. And then you have like batch size number of rows of this b vector, which is like kind of an array of b by n. And the reason I didn't use a capital B here is because I'm using that for batch size already anyway. To make this a bit simpler for us though, when we're deriving the backpropagation, we could write this as y equals small y equals small x, capital W plus b, where now x is just a row vector and y is a row vector as well, like this. So backpropagation, let's just quickly remind ourselves. So we have maybe like linear, let's ignore all other layers. Let's just say it's a totally like like concatenated linear layers for the whole network without any non-linearities, which doesn't really make sense when you're trying to do actual machine like neural networks, but it's okay for this discussion. And then maybe these go into like one neuron here, and then this computes like a loss somehow. And let's just assume that where we know the partial derivative, so this is, let's call this y here, and let's call this one x, and we know the partial derivative of y with respect to, sorry, the partial derivative of the loss with respect to y. And I'll come back to how we already know that, but we'll assume we know that. Now, I'm going to use red here because there are three things we want to calculate and we don't have, but we do have dl by dy. It's partial L by partial y, but I'll say d to make it easier for me. So we want, I mean, primarily we want dl by dw here, right? Because and then we want dl by db. We want these two because we want to then, as a like for a stochastic gradient descent, we know the gradients of the loss with respect to the parameters, and then we want to do a step in the correct direction towards the decreasing towards the negative gradient. But we also want dl by dx, and the reason we want that is because after we're done with this backpropagation step, this will become our new y here, and this will become our new x back here. And then this dl by dx will become our new dl by dy that we know. Now, when you look at the derivation of this in some of the places, they'll call these like, maybe they'll call this something like xl, and this will be xl minus 1 and xl minus 2. But I don't want to complicate myself with, thinking about more than one layer. Or the transition from one layer to another. So we need these three. These two because we want to do stochastic gradient descent. This one because we want to continue to calculate these two, but back here. And so then it's just by induction that if I'm able to get from here and go backwards along here, then as long as I can compute the first gradient here, which you all know we can, I can get from here back to here. So this is how we know. I promise I'll tell you this is how we know the dl by dy in the first place. Okay, so let's go through now and calculate all of these. I'm going to start with dl by dw. It's probably the hardest one. And once we've done that, the rest will kind of unravel. Okay, so dl by dw, well, actually, first of all, and I'm going to use this tool for all of them, I want to write this expression here, but just kind of write it out in matrix form. So y is y1, and I'm going to start my indices from, or indices from 1, so that I can go to yn without the n minus 1 there, equals x1 through to n, xn, and then this matrix, which is the weights matrix, and that will be w11 all the way through to w1n, and downways it will be wm1, and then in the bottom right corner here we'll have wmn. So that works because this is, here we are, I've made a mistake, xm. So this is m long, and it needs to dot product with the first column to get the first element of the y's, and that works because the columns are m long as well. And then plus b1 through to b capital N now. Okay, so back to where we were before. Let's look at dl by dw. Now, if we think of the chain rule, and we just forget for a moment about trying to match matrix dimensions, this, like, we just think it's like the scalar chain rule. This looks like dl by dy, which we know, this is the green one here, times somehow, some operation, depending on like what these look like, dy by dw. There we are. Right? Now, dl by dy, we can write this out further, is just dl by dy1 all the way to dl by dyn. This is a little more complicated because you have, this is like a row vector here. The y's are row vectors, and this is a matrix, so this will be like a 3-dimensional kind of object. So it's easier to then think about instead of this whole thing at once, just think about, wait, what does this look like, dl by dw? And that looks like this. It's a matrix which starts with dl by dw11, goes all the way to dl by dw1n on the right, and downways goes to dl by dwm1, and then this way goes to dl by dwmn. Cool. So let's look at these individual matrix entries here and see if we can then somehow figure out how to collapse this kind of complicated expression here with, you know, lots of dimensions here into something simpler. So let's just look for now at dl by dw11. And we can then do the same chain rule idea. So we can say, okay, we take this dl by dy, or actually I'll just copy this down, right? And this is now dy by dw11. So let's consider now what does dy by dw11 mean? Well, that is, we know that that is going to be a row vector itself. Sorry, a column vector, right? Because what do we expect here? This is going to be a scalar. This is a row vector. And the only way to get a scalar now is to have this as a column vector. We're also following the convention that if the vector's on the numerator here, so we end up getting a column vector when we do this partial derivative. So what does that look like? Well, let's just consider even more individually what dy1, so this is the column vector dy1 by dw11 all the way down to dy1, dyn by dw11. So what does this column vector look like? Which is, by the way, so I'm just going to use color for this so that you know what I'm talking about. So these are all blue, right? So now this is, okay, so let's just look at our original expression here. What is dy1 by y1 by dw11? Well, that is going to be x1, right? Because we get the only way that w11 is ever involved here is this row vector dot products this column vector here, and that ends up giving you y1, and the coefficient of w11 is x1, so you get your x1 there. Whereas dy2 by dw11 is going to be 0, because w11 is never involved in calculating y2. So these are all going to be zeros all the way down, right? And then when you then go back here, so this is x1 followed all by zeros. It means we end up like multiplying all of these by zeros, but we keep the first one. So the result, which is a scalar, will be dl by dy1, which we know is a scalar, multiplied by x1. That's what dl by dw11 is. So I'm going to do the rest a bit faster. So now what's dl? So we can actually even erase this here and put dl by dy1 x1. What's dl by dw12? So we're going to step up in this direction because this is where the w12 would be, right? And to do that, we just have to consider again our original equation for the forward pass, and we have to consider that this actually looks like this row vector here multiplied by, and then I'll just do everything in blue again. Oops. Like this, but instead we'll have a dw12 here. And then this will all be dw12s. And if you go through this, you'll find that the only thing that's that actually like w12 influences is when you multiply this row vector by the second column here and get your y2 back, right? So you will get that this is 0, dy1 by dw12 is 0, and then that dy2 by dw12 is x1, and then the rest will be zeros, right? So that ends up giving that this expression here is equal to dl dy2 now by x1. And then if we go fill this in the matrix, actually we go all the way to the right and we follow the pattern, this will be dl by dyn x1. So what we do is we step towards the right is we step the index on the y's on the denominator here, but we keep it all as x1s. We could have gone down instead now. So we could go to w21. So we'll calculate dl by dw21. And that will be equal to, and then again, I'll grab this whole thing here, paste it down because it's the same thing. And then I'll use blue here. And now I'll have dy by dw21 this time, right? And that looks like dy1 by dw21 all the way down to dy n by dw21. And that will be a bit different, because now if we look at our matrix here for the forward pass, W21 here, what we end up getting is that we W21 is only ever involved in calculating Y1. That's when you do the dot product of this row vector to this column vector. And what comes out, the coefficient that comes out is x2, not x1, right? So this will be x2, use my blue again, x2 all the way, and with zeros all the way down to the bottom, right? So this, this here will be dl by dy1. Oh, wait, so let me just finish this calculation here. So this will be this dot producted with this. So that's going to pull out dl by dy1 x2 now. So dl by dy1 x2, right? So what we do now is we're not stepping the y index, we're stepping the x index. So if we go all the way to the bottom, we can rub this out and replace it with its actual expression, which is dl by dy1 x m. And then this will be dl by dy n x m. Okay, so now we have what dl by dw looks like. And I'm just going to copy paste that down here. I still want to, I'm not done yet because I still want to get it looking like this, because I know what my dl by dy is, right? So I want to pull that back out again. But if you look carefully here, what you'll notice, and you can pause the video to try to figure it out yourself, or after I've shown you, but it's just, this is the outer product of the x vector and the dl by dy vector. Like that. So first element here times first element here gives you this element here, and then x1 by the next one, x1 by the next one, and that will give you the top row of this matrix, and then you do the x2s, right? So this is, and then remember this is like a m by 1 matrix, and this is a 1 by n matrix, so the product will give you an m by n matrix, which is what we expect for dl by dw. And then if we write that out again, that's just x transpose, if we considered x to be like a row vector before, and then your dl by dy. And this is your expression, dl by dw equals x transpose dl by dy. There's one more question here, is how do we get back to the batch version of it? So let's just think about that for a moment. So with a batch, all we're going to do is, okay, I'm going to use a different color here for, like, this, say this is the first batch element. Then this is the next batch data point or element. And I've used the same notation, and rather than changing notation for the second element, I'll just change the color, right? And then that will be the second batch element, and this will be the third batch element, and I'll just make that purple. And you'll just be adding all of them. And just think, why is that the case? Why are you adding them all? Well, we're looking at the total loss here, so the sum of all the losses associated with each of the batch elements, right? That's why we're adding them. Now, this ends up equaling to being x transpose dl by d capital Y, so the matrix Y. And to convince yourself of that, just look at, well, what bx transpose is. It's x1 through to x m, and then it's the blue version of that. So I'm being lazy with notation, so I'm just using colors. And then the purple version of that, x1 through to xm. Matrix multiplied by dl dy1 through to dl dy mn. You can pause this and convince yourself that this is the case, that if you were to matrix multiply these, it would be the same as taking the first column and multiplying it by the first row, and then adding that to the second column, dot product with the second row, and so on. So this is how you get this expression here. Okay, so let's do the next one now. And the next ones will be easier. So I've gone and deleted all that working from before because we have the answer here. We're going to look at DL by DB, and I've just kept this expanded form of this expression here. Okay, so DL by DB. Get my black pen back. DL by DB. And let's use that chain rule idea again. So that's kind of like DL by dy somehow multiplied by dy by db. And we know DL by dy. Let's think about what dy by db looks like. And I'm just going to focus in on that for a moment. That looks like this matrix here. dy1 by db1. Here we are. Now, dy1 by db1 is just 1. dy2 by db1 is 0 because they just never interact. And then you'll see that all of these are zeros. And actually, if you keep working through this, you'll just see that this is the identity matrix. Because this is element-wise addition, right? So the B1's only ever going to add on to the Y1. The B2 is only ever going to be incorporated into the Y2, and so on. So this is the identity matrix. So this is I. So it's actually quite uninteresting, really. The answer becomes dl by db equals dl by dy, and that's it, basically. There's one more thing that has to be done here, though, because dl by db is a row vector which has n elements, and dl by dy is also a row vector which has n elements. But when we when we go back to the batch version of it, we have something like dl by db equals dl by d capital Y. And now this is a b by n. And we just have to think about what's happening when we expand to the batch dimension. It's kind of like last time. This is just the sum of the losses of every single batch element. And so what we actually need to do is just remember that this is a matrix that has our dl by dy1 all the way to dl by dyn. And then this repeated, but for the different batch elements. So what we actually need to do is sum over the columns here. So and then we end up with one vector like this, which looks like, I can just write that expression, and I'll go ahead and write it up here. So this is going to be sum over the batch of dl by dy1, sum over the batch dl by dy2, and so on. Right? And you should put another index in here, which is like the batch index, if you're going to use proper notation. All right, so now the last one, dl by dx. Again, we'll write the chain rule. That's like dl by dy by dy by dx. So now we need to figure out what dy by dx looks like. Let's just focus in on that with blue. That looks like this matrix dy1 by dx1 all the way through to dy1 by dx n. Let's just verify those matrix dimensions. So this is a n by m matrix. So this is n by m. This here is 1 by n, and we expect this to be 1 by m, and that's exactly what we get by multiplying those out. So now let's just figure out what this looks like. So dy1 by dx1. The only path that we have to influence y1 by the right-hand side is when we do a dot product between this row vector and the first column here, and particularly when it's x1, it's just the w11 coefficient. So that's the gradient there. Wrong color. Now, we can ask ourselves the same questions for dy1 by dx2, right? The only way that y1 is influenced again is by the dot product of this row vector and this column vector, but now it's dx2, and that ends up interacting with this w21. So the w21 is the coefficient of x2 is the better way to say that. And then we can go all the way to the right until we get to m1. We could also look at dy2 by dx1, here, the next one down from w11. And we could ask ourselves a question, how is y2 formed? That's by dot producting this row vector into the second column here, and the coefficient of x1 for that would be w12. And we can actually follow that down until we get to w1n. And then this will end up being wmn. Now, if we compare this with this matrix here, we realize that this blue one is the transpose version of the black one. So we can now complete our expression. It's dl by dx is equal to dl by dy, and then this is actually just w transpose. So we're almost there. Last step now is to elevate ourselves to the concept of batches. So from small y to big Y, from small x to big X. So we have dl by d big X equals dl by d big Y. And what this turns out actually being is W transpose again. And the way you can think about that is that all you're going to end up doing is the same kind of operation each time around, because W doesn't change for each batch element. So the weights applied to each batch element are exactly the same. We can even try to just look at the indices for that. So dl by dx will be this matrix, which will have our first dl by small x here, right? And then our second one here. I'm not going to use colors, but you know that these are different. These are different dl by dx's, right? And then our dl by dy will look similar, like this, and we'll go down the batches, and then we'll have our W transpose. So to get the first row here, we're going to matrix multiply this row with W transpose, and so on and so on. So you can see that that kind of extension is easy to the batch dimension. So to finalize, that's dl by dy W transpose. And these are your expressions here, and now you can just write them into Python if you're actually implementing backpropagation. And then remember that the next step, you'll turn this dl by dx into your new dl by dy over here, and you'll keep going. Now, I had to stop a few times while recording this, mostly because I lost track of things or lost track of indices. So this is the exact reason I made this video, because I find that if I'm going to do this again, I don't want to go through this whole ordeal again. At least maybe if I see the way I reason through it, that will just jog my memory. So I hope it's as useful for you as it was for me if you're ever implementing backpropagation from scratch. And thanks for watching. Till next time.